talk. So our last talk for this morning's session is by Justin Chulo from Grand Valley State University, who's going to be talking about modeling college campuses using spatial networks.
Yeah, thank you guys very much for coming. I really appreciate having all of your time. So my project, it was a research project done in the fall semester, and it was about modeling the college campus that I go to using something called a spatial network. I often will walk between my classrooms and get confused on the path that I should be taking from building to building. And so if you've all ever used Google Maps, it's a very, very efficient tool for getting from location to location. I thought that it would be great to have a tool like that, but for my college campus, make getting around much easier. And so this research project kind of culminates in that. So really, why model a college campus? The number one for me was to help students navigate the campus. I think that college can be a very confusing place for a lot of people. And I think having a tool like this would be great. It would be a great boost for accessibility for a lot of students. And besides this, we could also learn a lot more about the structure of the college's sidewalks. Colleges are a very walkable, I would say like location. They're a very walkable thing, right? You walk around, you don't often drive. So I think looking at the sidewalks is going to tell you a lot about the structure of that campus. We also want to use network theory and graph theory to our advantage. And we can write the sidewalks in the language of networks and graphs. We can use a lot of tools that other smart people have developed for us, and it can tell us a lot of information. So what is a spatial network? You can think about a network as just a collection of dots that are connected with lines. And we call those dots nodes, and we call those lines edges. Every single one of these edges are going to have something called a weight, and a weight is just a number that represents something in our network. In this case, you can see that the dots here are connected with an edge, and that edge has a weight of 2. And in a spatial network, these weights are going to represent distance. So you can imagine these on the Euclidean plane. You can think about these two nodes being 2 units apart. So when we're building a network of Grand Valley's campus, we want to think about the edges as our sidewalks, and we want to think about the nodes as the intersections of our sidewalks, where the sidewalks will meet in our path, and the weights are going to be the actual distances. And I did this one in meters. As you can see in our image right here, essentially our process was to add a node at every single crossing, and then we connect all of our edges and we will physically measure that. And so what assumptions are we making when building this model? More than anything, students are only going to be walking on sidewalks. We're assuming that students aren't going to want to cut through grass, they're not going to want to cut through parking lots, they're just going to be staying on sidewalks. Otherwise, we would have a lot more edges than we could really work with. We also want to assume that students aren't cutting through buildings. A lot of the buildings at Grand Valley might not be accessible to every single student, and adding the interiors of buildings complicates our graph a lot. So when modeling from getting to building, it's not going to shorten our path an extreme amount, but it's still an assumption that we need to be considering. And lastly, we are counting arriving at any entrance as arriving to that building. So if you wanted to get to the library, any door to the library will count as your journey has ended. So our process for this model was step 1, measure every single sidewalk on our campus. This was by far the most time-consuming part of our project. We used Google Earth in combination with a measuring wheel, which is the wheel with the stick that clicks as you walk. Doing that, we took about 6 weeks, I'd say, to measure every single sidewalk. And as we are measuring, we are entering all this data into Python. We're keeping this in a dictionary, and we're going to keep track of every single node, all the nodes that that node is connected to, and we're going to keep track, and we're going to keep track of the distances between these nodes. And since we're using Python, we're using 2 packages mainly, NetworkX, which is a graph theory and network package. It has a lot of useful tools that we can use for analysis, and Matplotlib for visualization, for making all of our pretty images. And then last, we want to analyze our data. So in that analysis, this is what we have for our model. As you can see here, we've got all of our edges as these little black lines, and I put a blue square for every single building on campus. Keep in mind, this might look like a map, but it's still a discrete structure. It's a collection of dots and lines that are connected to each other. So using this structure, we can actually tell a lot. And the number one thing I wanted to do was build a wayfinding program. So this wayfinding program, we have to find the shortest path between any of these 2 buildings. As you're looking back on our map, We want to find the most efficient path between, let's say like this blue square and this blue square. There's an infinite amount of paths, right? Which one would be the best? We use something called Dijkstra's algorithm. And Dijkstra's algorithm will essentially, you give it any 2 points on your graph, it's going to tell you the shortest path. And to build this website, we use JavaScript and a Google Maps API, which I actually ran out of my free trial for. So as you can see, it says for development purposes only, but what you do is you can enter in any starting location, like for example, all the math classes are in Mackinac Hall, and let's say someone lives in the South E Residence Hall. Then you hit calculate route, and we're able to find the shortest path between these 2 buildings. I think this is a really, really cool tool. I'm very, very proud of it. But after we built this tool, we still had a lot more time in our research, and I figured we have this really cool structure of nodes and lines. We can do more than just, we can do more than just build this program. We can actually analyze the connections and maybe tell some other stuff. So the big 4 questions we really wanted to answer are, what is the center of campus? Where is it? We want to know what is the most important sidewalk, a sidewalk that if it were closed would extend to everyone's day. We want to try and evenly separate our campus into different sections, maybe looking at clustering our nodes. And we want to be able to tour every single building efficiently. So first of all, we looked at the center of campus. We use something called node closeness centrality. When you're looking at this, you pick any vertex, and you find the average shortest path to every other vertex. So I would find the shortest path between these two, these two, these two, these two, and I do that for every single pair of nodes. And then you average them all up, or rather you add them all up, and the longer your paths are, the lower score you have, because it takes longer for you to get to every other node. And doing this, you can see that we have a very clear cluster in the middle of our graph, right? And that actually correlates to the Carilion? The good clock tower. And I think that's, is it Carolyn?
I think so.
To the clock tower at Grand Valley, right? And I think it's really, really interesting. Historically, the clock tower was one of the first buildings that was built at Grand Valley. And it kind of makes sense that that would be at the center, because when you were building, you're building outwards, right? You're not starting around. So I think that's kind of cool. Historically, it makes sense. We also looked at another kind of centrality called edge-betweenness centrality. And the main idea of edge-betweenness centrality is we calculated every single shortest path between 2 nodes again. So we picked every single combination of 2 nodes, and we found the shortest path. If our path goes through that edge, we're going to give it a point, right? So the more often that an edge is used in the most efficient path, the more important it is, right? So looking here, there are 3 main lines that you can follow. It's a little hard to see because the lines get a little small, but there's one main path going through here, and it splits off all the way kind of cutting through campus. And as you may see, the most yellow edge is right here, and that correlates to the Little Mac Bridge. And I think it's really, really interesting because over the summer at Grand Valley, the Little Mac Bridge was actually closed, and it really did put a damper on my walk to and from class. I think it's really, really cool that Grand Valley could maybe look at this and say, okay, if we are going to be closing this bridge, we're going to expect more foot traffic going this way. Or if an advertiser wanted to advertise like for a club or something, they should go to one of these yellow edges, because that's where more people are going to be taking shorter paths, right? We also looked at something called clustering. And clustering, we essentially want to group our nodes in groups where each node is similar to each other. And when I say similar, I'm thinking of their proximity. So when I'm looking at my map, I have the XY coordinate of every single point. So I imagine that each one of these nodes plotted on the XY plane, and we want to cluster with that. We want to make sure we have a good clustering, because we could cluster everything in one cluster, and that's technically right, but we want to find out what is a good way to cluster. And our clustering algorithm that we used is called K-means clustering, and to think about K-means clustering, the K represents the number of clusters. So now the question is, how many clusters should we use? We use something called silhouette scoring, which basically tries every single number of clusters. So as you're looking at here, we tried 1 cluster, 2, 3, 4, on and on and on. And our scoring is going to be if a cluster is dense, so there are a lot of points in that cluster that are close together, and if it's separated, if the clusters aren't dense and on top of each other. because if they are, they should just be the same cluster, right? So the higher your silhouette score, the better your cluster is. And as we see here, I find it interesting, Grand Valley is clustered well in multiples of 6, 12, and 18. I thought that was pretty interesting. So we want to focus on 6 and 12 because 18 might be a little much. So clustering into 6 clusters and 12 clusters, we get this. And these stars are just going to be the centers of the cluster, but I really want to focus on the similarities between these two. You can see that the clusters in 6 split up into different individual clusters in 12. I thought that was quite interesting. Another thing that I thought was quite cool is looking at the 6 cluster. If you know Grand Valley, you might realize, or you might recognize that this is the Kirchhoff residential area. This is going to be a lot of our academic buildings, the library, the main food dining area. We have a lot more academics here. This is going to be all of our athletic buildings. This is more residential, and this is like the south apartments. I think it's really interesting that mathematically clustering our campus already mirrors what we have zoned our campus into. You can see it gets split up into the academics, the residential, athletics. I think it's cool that that's reflected in the buildings that are actually there. My map doesn't care about what's there. All it knows is that there are dots here that are connected with these lines. But clustering it anyway, I think it's cool that that's reflected. Even looking here, it gets even more refined. You can see mapped in a hall here. We get even more of a group of academic buildings, residential buildings, athletics. I think that's quite cool. We also wanted to answer a version of the traveling salesman problem, if you guys are familiar. So the traveling salesman problem asks if there's a salesman who wants to visit a certain amount of cities. Let's say that he lives in Grand Rapids, and he wants to try and sell a car in Grand Rapids, Mount Pleasant, Lansing, and he wants to do that in an efficient way. What is the best way for the salesman to travel to every city and end back where he started in a closed loop? So essentially, we want to think of this in the context of Grand Valley as a student starting in some building, visiting every other building, and end back where they were in an efficient closed loop. So, as you might know, this is an unsolved problem, and there's no real better way to actually get the real solution besides trying every single closed loop. And that is nigh impossible with the amount of edges and nodes that we have, so we use an approximation. And with our approximation, we use the Christophil's algorithm, and we saw that this right here is a path for visiting every single building on our campus. The way that you read this is you start at any point and you follow along the color. So here, we start in Lubber Stadium, our football stadium, and you can follow all the way down and south. I think it's interesting that one of the most efficient paths that you can take to visit every building crosses over on itself. It doesn't just hit everything like this and go around. It's almost crisscrossing in this S shape. I think it's quite interesting. I think a really good application of this would be like emergency services. Let's say there's an emergency on campus and you need to check every single building, make sure that everyone's safe. You should do that in the shortest path possible, right? Another way that you could apply this, let's say if you wanted to visit every single academic building. This was supposed to cross that out, it's a shame it didn't, but we wanted to visit every academic building. You can think about a college tour, right? You want to be able to tour a certain amount of buildings. And if you're walking for a very long time with a large group of people, they might get quite confused on campus and you're going to be tired. I think finding the shortest way to do that would be super useful for Grand Valley to know, or any college campus. And you see here, it's the same thing. You're crossing over on yourself. I think that's quite interesting. So, essentially, I think that spatial networks are a really powerful model that I don't often see used to model buildings or college campuses. A university would really want to know a lot of this information, like the most efficient routes. Let's say you want to plow the snow at Grand Valley. Knowing how to quickly travel between all of these buildings in an efficient way is going to be super useful for a university to have. The same thing with planning campus events and emergency services. There are a lot more things that you could do using tools from network theory. I think it's really, really interesting, and this model can be applied to any college campus. There's nothing specific about Grand Valley that makes this work. So I think that overall, this model, I think it's a very, very cool tool. For future research, I would really want to look at accessibility, seeing how our model changes based off of how people travel around campus. Let's say that there's a person who uses a wheelchair. How is their path going to be different than a person who can walk a lot more easily around campus? Maybe my most efficient path is not the same as them. Same thing with looking at the interior of buildings. Being able to model the inside of a building, I think, would be very, very useful. I mean, I'm sure we've all been in a building that we've been very confused at where our classes are. A tool where a student could find the path from their car in the parking lot directly to their class, I think that would be a really, really powerful tool that a lot of people would be very interested in. Same thing with looking at the structure of a parking lot. Parking can be a big issue for a lot of people, and I think that if we can score how efficient a parking lot is, that would be a very powerful form of analysis. I think it's very, very interesting. And yeah, I really want to thank you guys, and I would especially like to thank Dr. Bailey, my mentor on this, for unending guidance. Thank you.
And we've got about 5 minutes for questions.
Yes.
So you mentioned that the traveling salesman algorithm is particularly computationally expensive.
Yes.
And inefficient. What were other areas, a lot of these discrete math theorems, minimum expanding tree stuff, they are computationally very expensive.
Yes.
They might not necessarily behave in polynomial time. So what, if any, challenges did you face in the computationally expensive process?
Yes, we had a lot of other things that we wanted to look at, including if Grand Valley was going to add a new sidewalk, what sidewalk should they add to shorten the average path the most? And what we ended up looking at is we looked at every single node that was 2 away. If you imagine a node being here, connecting to this one, connecting to this one, would it make sense to add a sidewalk here? The way we did that is we looked at every single node and its neighborhood that's 2 away. And we connected that node to that node. That is a lot of possible sidewalks that we could add, and it ended up taking so long that we decided that it really would be worth it to spend our focus on other places. But in the case that there are more efficient ways to do this, or we can think about this problem in a different way, I would love to do more stuff like that. But yes, it is a problem that you often come up in combinatorics. It's just, you have to check a lot of things. But yes, I ran into that problem a few times. Good observation, thank you. Yes?
It's a little similar to this, but let's say you were to add a building to the college campus. Is there a way you could apply this to determine how many and where those added sidewalks should go to add a building?
Yes, we looked at if you were going to add an emergency services building, well, you would want that building to be able to get to every other part of campus quickly, and you would look at the node closest centrality to do something like that. As for adding sidewalks to that building, you would most often see the building connected to pre-existing sidewalks. So I think that in the case of adding those sidewalks, it would affect our shortest path. As you can see here in edge between us centrality, there's a very big dependence on this bridge alone. If there were, say, another edge that connected from here to here, I don't think this bridge would be as important because there would be other ways for students to get across. You know what I mean? So I think that adding those sidewalks are going to affect our graph, and I think that the way we have set our data up, it's very easy to add edges onto our data because, I mean, things are always getting renovated. It's Michigan, so construction is a natural part of our lives. I think that it's a very important thing to always be adjusting your model. Yes?
Okay, so you've got these edges that are
Yes.
bright when they're the most traveled, which are maybe not the most traveled, but the most helpful.
Yes.
But then it seems like this would make them have the most traffic and therefore increase their distance.
Yes.
Is there any way of like analyzing that?
So you can think of this in the context of like a flow problem. You can imagine these as pipes and looking at how traffic, if it were like water, would flow through these edges as if they were pipes. You could use a lot of network flow things to analyze this, but that's a good thing that I should be looking into. That's a good point, yes. But you could adapt this model slightly to change it into that, but I think that the fact that more people use these edges would affect how helpful they are. But I mean, by definition, a helpful edge is used more often, right?
Yeah.
So I think that's a good, yes, that's a good observation. Thank you.
Have you tested it on any other campuses?
I have not. It takes a very, very long time to measure all of these sidewalks. And if a campus were to have that data already in perhaps like a GIS file, if you're familiar with ArcGIS, it's a geospatial information spacing software, something like that. It's a software that's built for locations in metric spaces and holding on to that data. So if a campus were to already have that information, it would be much easier to build this model. But no, I have not personally applied this to any other campus.
Do we have time for one more quick question?
How does Google Earth do it then?
So Google Earth does it using, well, the thing is, Google Earth doesn't have like finer details like a sidewalk more often mapped, or Google Earth will be a little bit more inaccurate with sidewalks. It's very, very good with road data because road data is very heavily monitored and every city knows where their roads are and how long they are. But a college campus, like I went to the facilities department at Grand Valley and spoke to them if they had this data, and they didn't. So cities, they have a lot more importance to that data. But for this, yes, I had to measure all my own. And Google Earth, I would imagine, pulls from those cities' data.
Well, let's thank Justin for his talk.